more precise manner. Okay. I just speculated the definition. Well, I should have seen to the notes. Okay. So I have a parametric curve that is a subset of Rn, and P is a path, and C is an image of that path actually. Okay. In addition, this P, this path P, should have following two properties as well. So it must be piecewise smooth. Okay. So it must be piecewise smooth. So what do you mean by smoothness of it? So it means that this derivative, okay, so the derivative exists. Okay. Derivative exists, and this derivative exists. So not only exists, but it is continuous. Okay. At at all points in I, and I must write except finite element. Except there can be the finite number of movements in the curve where the curve or the derivative or maybe like this condition fails actually, because that's why you are calling it piecewise. Okay, so so you have a domain and you are mapping over it. Okay, there may be some finite number of points over the intervals where the function is not continuous or differentiable, but they must be finite actually, not more than finite. They can't be infinite. So that's our one of the fundamental assumptions. Is the second assumption is that it must be regular. P is regular. That is that P prime of P must not be 0. For all P in I except maybe finite P in I, because we are talking about not regular but piecewise regular, I should say. So now can you see the difference between both properties? So here you are saying that it must be smooth. It means that function should be continuous and differentiable. But it doesn't mean that it can't be 0. It could be 0. But now you are removing that glitch. Actually, you are saying that it must be regular. In other words, that it shouldn't get to 0 actually. It shouldn't get to 0. So for example, one of the curve that you can have could be something like this kind of a curve. So this also would be a kind of a path. So what points are going to be the trouble-making points in this curve? So the cups, because via these kinks actually, whatever to call it, the kinks. Okay. These duplicity points, they may also be, trouble-making point. Okay, so not necessarily, but maybe these are the things that we must think about them. But the kinks are something. So, if you wish, you can treat this entire function as. So, if I want to treat this as what? If I want to see this entire path, then I can see this as the combination of the pieces. So that's one piece. Okay. This point must be excluded from the domain because here it's not regular, and that's another piece. Okay. Okay. If this point where it cuts itself is a troublemaking, just throw it out. Okay. And then that's another piece. Okay. Here the function is continuous and differentiable. You can differentiate that. And if you, for example, compute the derivative of the path, and what would be the meaning of a derivative of a path. So if path is representing displacement, the derivative is velocity. Or velocity is what? Is really tangent to the vector actually. Okay. We know that velocity is nothing, it's just a tangent. So you can compute the tangent vector at any point in this curve actually. This will be a troublemaking point. Okay. The rest of the points are smooth actually. Okay. So that's one of the critical, maybe idealistic kind of assumption actually. Okay.
सर अभी भी सर मसला है सर।
हाँ बताइए।
सर वो हमने कहा कि सर स्मूथ है, सर कंटिन्यूस भी होगा, डिफरेंशिएबल भी होगा। जब हमने ये कहा तो सर उसमें से जो कॉर्नर थे वो तो चले गए ना सर।
कॉर्नर जो हैं क्यों जाएंगे? So a continuous function may look like this actually. So this is also continuous.
और हम कह रहे हैं सर वो डिफरेंशिएबल भी है सर।
नहीं, but when I'm saying that, okay, so if I'm saying this, okay, the important thing that you must realize that I'm not calling it a piecewise continuous. I'm not saying that treat entire function as a one continuous piece, but I'm saying that, okay, think about this piece. So exclude all these points. Okay, exclude all these points. Okay, except all these points. If you treat this as a piece, then this function is not only continuous but also differentiable. Okay, here the function is continuous. Okay, but you don't have a differentiability yet. So you're going to say on this piece you have smoothness because it's continuous and differentiable. Not at this point, because for smoothness you need quantity and differentiability. However, this path, so here you're going to say the function is continuous and differentiable, okay, both except this part. Can you see this? So that's what. So therefore you're calling it piecewise regularity and piecewise smoothness.
और सर अगर यहाँ से हम piecewise हटा दें सर, हम कहेंगे कि P हमारा smooth है सर, तो वो भी तो वही बात होगी।
एक ही बात होगी, but then you will exclude lots of things. So you are assuming that your curve is only like that. Okay. So you can't define integral over such kind of a function actually. You can't define integral over lots and lots of the curves actually. Okay, which can be physically a lot of important curves, but now you're going to say that now you have to exclude them. So the piecewise continuity and piecewise regularity and piecewise smoothness is making your set bigger, where you can apply this theory. That's what is the beauty. Huh? So if you just say smooth and some people do it, okay, they develop the theory and they just assume everything is smooth and regular and continuous and fine. So they don't care about piecewise smoothness and piecewise regularity and piecewise continuity, which is fine. I mean, if you wish, you can do it. But if I have this assumption with me, piecewise regularity and piecewise smoothness, then I can apply this theory to lots and lots and lots of very practical situations actually. Otherwise, I'll be limited with, I'll be always asking for the smoothness. I don't like kinks. So none of the curves with a kink, इस किस्म की किसी भी theory को, this will not touch actually. This theory will not touch. Imagine, so imagine I have a, for example, so imagine I have a tennis ball and I'm throwing it. What kind of curve it is going to be? It's not just throwing it. So it's going to touch, it's going to hit there and it's going to go up actually. That means you can't understand the dynamics of such kind of an object because you don't have theory. You don't have tools that allow you to study such kind of motion.
सर फिर तो ये जो इसने जो बनाया सर ये सर उसमें तो फिर ये हमारी कर्व की डेफिनेशन में भी नहीं आ रहा।
क्या मतलब?
मतलब ये जो गेंद हमें फेंकी सकी जो उसकी ट्रेजेक्टरी बन रही है सर।
So that would be this trajectory.
हाँ सर, तो ये हमारी कर्व की डेफिनेशन में आप
क्यों नहीं आ रहा?
हम इससे क्यों डील करें?
क्यों नहीं डील करें?
डील तो करें सर, लेकिन कर्व की डेफिनेशन में नहीं आ रहा।
क्या आ रहा है कर्व की डेफिनेशन?
कि हमने अज्यूम किया है कि वो जो हमारा पीसवाइज कंटिन्यूस होगा और रेगुलर भी होगा सर।
So continuous होगा सबसे पहले तो it will be continuous because it's path, okay, and it will be piecewise smooth, okay, So it can be non-smooth, but only at the finite number of points actually. Okay? It can be non-smooth. So my point is that if you force yourself to only deal with continuity assumption and smoothness assumption, and you don't allow such kinks actually, we are talking about a very small set of objects, very small set of curves actually. And it completely depends on you that if you are happy with such curves, fine. Okay. We'll not maybe deal with the curves with a lot of curves with the kinks actually. But we want to develop a theory. When you are developing a theory, you try to generalize it actually. Okay? You try to generalize it. You want to keep it general so that if there is a need, you can apply it easily. Otherwise, you have to redevelop the theory. You have to adjust things actually into your theory. ठीक है? आस्ते आस्ते आएंगी बातें समझ में. चलें. There is another remark about duplicity of a point. So in other words, a curve may intersect itself. So this definition is not excluding such kind of curve which may intersect itself. You can have a curve that may intersect itself actually. Okay, so this is important. Now, here is a definition. So I would like to define the next thing is reparametrization actually. Okay. Parametrization. Okay. So I'm with the basic definition. I'm a bit slow so that you can absorb it. Why the definition the way it is? This is important to understand. Okay. So I would like to define the reparametrization. So a curve, you can have a curve. So this path. So I have a curve. So imagine a circle actually. Imagine a circle. Okay. So how many ways do you know to represent a circle actually? Okay. So one is this. Okay. So you have this parametric equation: x squared plus y squared equals 1. Okay. So that's a parametric equation. That's a rectangular equation. So anything that's any x and y that satisfy this equation can represent this circle. Okay, so what is the most obvious choice for x of t and y of t? Okay. So if you're talking about, for example, a unit circle, it's going to be cos t and sin t. So it satisfies. So I'm going to say p of t, that is x of t, y of t equal to cos t, sin t, is a one path or a one parameterization through which I can represent the curve. But can you guess any other? Anything else? So imagine if I fix x to t. So let me take x to be t actually. And I'm interested in satisfying this equation. So what should be my y of t? Exactly. So square root of 1 minus t squared. Okay. The square root of 1 minus t squared. So q of t, that is t and the square root of 1 minus t squared, is another parameterization of the same curve. So you have a curve which has two parameters, and you can find lots and lots and lots of parameterization. So what could be another possible parameterization of this curve, for example? Exactly. So just take x squared to be t squared actually.
1 minus t
You're going to get another parameterization of it actually. So in other words, you have the same curve having different parameterizations. Question: is there a relationship between the parameterization actually? Sometimes it happens that you have this irregularity due to a parameterization, but if you change your curve from one parameterization to another parameterization, that difficulty goes away. Okay? So we need to understand, okay, what is the meaning of going from this parameterization to this parameterization. So if I know one parameterization of a curve, how can I know the other parameterization of a curve as well? Okay. And what would be the benefit of having the parameterized or the different parameterization of curve, that maybe one parameterization is missing some properties. Okay. And you can find another parameterization, okay, which is the parameterization of the same curve, but it just works. Everything is okay. Are you getting the point? So therefore we are having reparameterization actually. Okay? So we like to define reparameterization. So what do I mean by reparameterization? So as a definition, I'm sorry? किसका? ये खुद ही एग्जाम्पल है. I will. For example, ये जो cusp है, we're gonna fix it. We're gonna fix it. ठीक है? We'll fix the cusp. Okay.
तो यहाँ पर t की वैल्यूज भी होंगी ना चेंज.
क्या मतलब?
यहाँ पर जो t की डोमिनल है और ये जो स्क्वायर रूट के अंदर है.
Okay, you can.
Yes,
if I wish, I can fix t to be between 0 to 2 pi. Okay. So I can take interval to be 0 to 2 pi. I can take an interval to be entire r, which is fine. Okay. And that's another advantage of expressing through parameterization actually. So if I have just a simple equation, x square plus y square equal to 1, what does it mean? So you have a circle, a circle, and you started from a point and you just move along and reach to the point again, and that's it. That's what your x square plus y square equal to 1 is. But if you take the circle and represent it in this manner and extend the domain, so I'm not taking 0 to 2 pi, but I'm taking 0 to 4 pi. What does that mean? So you have moved twice actually. Okay. You can extend it even more, you can move even more actually. But with this rigid equation, this rectangular equation, it means that you just have this picture. So you can't see the dynamics actually. You can't see the motion in this. So even though there is hidden it, but you can't explicitly see it. So there are lots of advantages of doing the parameterization. So that P is a map from I to Rn, and it shall be a parameterization of curve C. What do you mean by being parameterization of curve C? It means that P is a path that satisfies all that. That's what I mean. That it's a path where the C is the P of a I, and P is piecewise regular, and P has smooth as well. That's what these are. So it's one parameterization of it. And reparameterization. Q. That is going to be a map from J into Rn, where J is another interval. Interval which satisfies this sense, so it must be open and all the properties that it must have, is So reparametrization Q of G is Rn is something like that. So if you want to obtain Q of T, okay, you want to reparameterize the curve, what you need to do, you have to map a phi. Okay? You have to map a phi, and that phi is a map from J to I. I'll make a picture of it. You will see what it means. So phi is a map from J to I. Okay. So when I evaluate the phi at t, so it's an element where?
In P.
In I.
I.
So it's in I because phi is a map from J to I. So take a t. So Q of t. So obviously this t must be from the J because Q has a domain J. Okay, and phi is a map from J to I. So the phi of t is a number that is throwing you into the interval I. And this guy, since it lives in the interval I, it's ready to be swallowed by P. Okay? It's ready to be swallowed by P. Okay? There is the point. Now, what properties this phi must satisfy? So, let me write it explicitly. Phi is a map from J into I that satisfies this. That this phi must be continuous, it must be piecewise smooth, so it satisfies all these properties. So it must be piecewise smooth and it must be piecewise regular. So if you have such kind of a phi, must satisfy another property. It must be smooth, piecewise regular, and it must be strictly monotonic. Do we understand what do we mean by the monotonicity? So it must be a kind of a function that is either always increase or always decrease. Okay? It's always decrease. Then phi of J must be the entire phi. It should be, what do you say, an onto map. Must be an onto map. Okay. So if you have all these